Okay, so what we want to do, we just saw that this always wins, this comes in second, this comes in last, right? And so it just has to do with the rotational inertia, right? And it makes sense, again, because something with a small rotational inertia, it doesn't take as much torque to get it going. So it's easy to get it rotating, right? Okay, but we want to prove it. It's a nice review of a lot of things we've learned this semester, okay? So what we want to do, we want to do what we just did, right? We want to roll various objects down a ramp, and we want to calculate the final velocity. And whoever has the fastest final velocity wins, right? Okay, so that's what we're going to do. Now, we have a starting point and an ending point, right? Now, a few minutes ago, I asked this question. Let's see. Yeah, this one, right? And it was simple because mechanical energy was conserved, As soon as we see that frictionless, we jump for joy, right? So we just use mechanical energy conservation, piece of cake, doesn't depend on mass. So, but now we're rolling things. But wouldn't it be great if mechanical energy were conserved? There wouldn't be so much work, right? So let's think about it. So what do? You go to the energy equation that, the long energy equation that has everything there is to know. There it is, remember? Okay, so let's see if mechanical energy is conserved. So the system, the system involves the object, the ramp, and obviously we're going to include the Earth because we want to have gravitational potential energy. Okay, so any external work. I just dropped the thing and let it roll. Any external work? No. All right, good. Okay, so that goes away. How about this? W dis. Well, what are the forces acting on the thing? Well, there's a normal force, right? There's a normal force. Does that do any work? Well, that's not even a dissipative force. I don't even have to care. Forget it. But it does no work anyway, but we don't need to talk about it, sorry. Okay, W dis is like friction. Is there friction? Of course there's friction. Right? There's friction. But wait a second. The work done, remember, here's the equation, right? Right? Okay. When this thing is rolling, that's where friction acts, at the bottom. Is this thing moving? What did we learn? Remember the pictures of the bicycle wheel when it hits the ground? What's the instantaneous velocity right there? 0. So therefore, what's ds right there? If it's not moving, what's ds? 0. So what's the work done by friction when something is rolling? 0. So therefore, what's the dissipative work? 0. Okay? So isn't that awesome? So that means that this goes away and this goes away. So that's why we had to talk about the velocity being 0 at the bottom of the wheel, because that allows us to throw this away. So that means mechanical energy is conserved. How awesome is that? So we don't have to get all fancy and complicated. We can just use mechanical energy conservation. So that's all we're going to do. But we have to remember that when it's rolling, there's 2 terms in the kinetic energy. But that's not a big deal. So we'll just do it. All right. So U initial plus K initial equals U final plus K final. No kidding. Right? Okay, K initial is 0. U initial is 0. Right? So that's all we have. But K final, remember, there's 2 kinds of kinetic energy. So we have, all right, so let's do it. So what U initial is just mgh, or mgy, whatever you like. K final is 1/2 mv squared plus 1/2 I omega squared. So that's all. That's awesome. Now remember, we're trying to solve for v, right? We want to see who has the fastest v. But here's a v, but here's a v also. It's just hidden, remember? So we better take care of that. So v equals r omega, therefore omega equals v over r. So we better substitute, right? We better, because we're trying to solve for v. So instead of having omega squared, we can have v over r squared. That makes good sense. All right, awesome. Now we're going to do a little trick. It's not really a trick. We're going to make things easy, but that's kind of a trick, I guess. I don't know. Look at that. You notice that every single one of these I values, it's always I equals some number, some coefficient, a 12th, a third, whatever, times a mass times a distance squared, right? Every one of these is always a number, what I call a coefficient, times a mass times a distance squared, right? Now what differentiates this between that and that and that, you know? What's the only thing that's different about these? The coefficient, right? Because again, they're all mass times a length, but it's the coefficient that's different. A 12 to 12, you know, all this stuff, right? So let's just solve for the coefficient. You'll see why, all right? You'll see why. So the coefficient just equals I over mr squared. And that's going to be incredibly useful because, again, it's the coefficient that differentiates between them. So let's do that. So we've got to get a different color. All right. So in other words, I want to get that coefficient in my equation. I want to do that. Nope, piece of cake. Why do you mean piece of cake? Well, let me just rewrite this a little bit differently here. So it was I v squared over r squared, right? Okay, so that, all right, I just took away the parentheses. Big deal. Now, I want to get that coefficient somewhere. So I want to get a I divided by mr squared. Well, here's an I divided by r squared, but I want an m. So put it, right? So we can multiply on the bottom by m as long as you multiply by the top by m, right? That's just good old algebra. So let me write it a little bit differently. So now I have mgh equals 1/2 mv squared plus 1/2, I'm going to say mv squared times I over mr squared, right? I didn't cheat. I just, you know, kind of changed it around. All right? Now, hey, wait a second. I have 1/2 mv squared here and 1/2 mv squared there. Well, gee whiz, let's factor it out. What do you say? So I have mgh equals 1/2 mv squared times 1 for this plus this, I over mr squared. Right? But, wait a second. What is I over mr squared? It's that coefficient. That's right? And that distinguishes between the disk and the hoop and the sphere, you know? So I'm just going to put here, so I'm going to say mgh 1/2 mv squared, 1 plus the coefficient. Ah, that's good, right? That's awesome. Okay, now what am I supposed to be solving for? I'm supposed to be solving for v. Okay, first of all, get rid of the m's, right? Get rid of those m's. Multiply by 2. Divide by the 1 plus coefficient. Take the square root. Whoa! So I have velocity equals 2gh all over 1 plus coefficient. Square root of. All right? So that's my final velocity. All right? That's my final velocity. Yeah, you can do this in lab, by the way. Probably on a test. Okay, now I'm going to show you why it was totally awesome to write it this way with the coefficient. Okay, let's do the velocity of the sphere. And let's just leave the top 2gh, right? Because it's going to be the same for all of them, so we might as well, right? Okay, so the sphere is going to be 2gh. And it's 1. Okay, what's the coefficient for the sphere? 2/5. 2/5. 1 plus 2/5. Okay, what's 1 plus 2/5? 7/5. So it's going to be 7/5. And that's the same thing as, all right, divide fractions. 5 times 2 is 10. 10gh over 7. Agree? All right. So, and that's the same thing. Okay, so you take the square root of 10/7. I did it, and that's 1.2 times square root of gh. All right. All right? So that means that no matter what, the final velocity of a sphere is always going to be 1.2 times square root of gh. Okay, awesome. Let's do the disk, right? Let's do the disk. Velocity of the disk. 2gh. Okay, 1 plus coefficient. Disk coefficient is 1/2. 1/2. What's 1 plus 1/2? 3/2. 3/2. Invert and multiply. You get 4gh over 3. All right, I promise you, you do it, and that comes out to be 1.15 square root of gh. All right? Let's do velocity of the hoop. Two gh over 1 plus coefficient. The coefficient is 1. So it's 1. So that means we have 2 on the top and 2 on the bottom. Goodbye. Right? So we just have square root of gh. So we just have equals, square root of gh. Okay. So which one is always going to win? Which one has the fastest speed? This one. Is always going to win. Which one is always going to come in second? Which one is always going to come in last? There you go. Did that exactly match our results, our experimental results? Yeah! All right? And look does it depend on the mass? Not at all. Does it depend on the size? Not at all. All right? So that's what's awesome. So this is a neat little exercise here because you use that big, long energy conservation equation. You have to realize that the velocity is 0 when the rotating object hits the track. You have to use mechanical energy conservation. You have to use both kinds of kinetic energy for rolling motion. I mean, this has a lot of good stuff, right? That's why I like it. So you may see it again. Woo! All right, so that was cool. Okay, let's see. Center mass, kinetic energy. We did rotational force. Rotational, I already said that. We haven't done angular momentum yet, right? We haven't talked about the rotational version of angular momentum. So let's do that. Angular momentum. We've done translational momentum, P equals mv, but we've got to do angular momentum. And boy, you use this a lot using quantum mechanics, Quantum mechanics is the physics of small things, so you're going to use it in chemistry, quantum chemistry, all over the place. All right, angular momentum. Oh my gosh, here we go. Okay, here's linear momentum. So translational motion, right? P equals mv, no kidding. And for the rigid body, all we have to do is substitute the velocity of the center of mass for the velocity. So that's nice too, right? We like it. Okay, now, angular momentum. So there's a bunch of different equations, there's a bunch of different circumstances. Okay, so let's say we have a particle going in perfectly circular motion. So as we've seen a million times, this is R, this is V, perpendicular, right? Okay, so they use uppercase L for angular momentum. And it's a vector, but I'm just giving you the magnitude right now. Okay, so if it's a particle, it's going in circular motion, here's the equation. Angular momentum equals RmV. That's kind of nice, because mv is just p, regular momentum, so it's rp. And this is simple to remember, because when you think of a circle, what do you think of? The radius, right? And so the angular momentum is just the radius times the regular, ordinary translational motion momentum. Oh, that's cool, right? RP, RmV. Okay. Well, I mean, it's true, but we don't really use it a lot. Okay? But, I mean, we could, right? Something on a turntable or something like that, Okay, here's another one. This is the general one, okay? Any type of motion about an origin. So here's the origin. Here's the particle. This is the position vector. This is the velocity of the particle. It has angular momentum. Any kind of motion about an origin has angular momentum. And look at the equation. Oh, my goodness. L equals R cross P, vector cross product. So there you see it again, that vector cross product. So you got to know how to do the vector cross product. Okay, sorry. All right, let's get an equation for this. Let's get an equation for just the magnitude, okay? The magnitude of L. And I don't want to use theta in my equation, okay? So what's the magnitude of a cross product? The magnitude of a cross product is the magnitude of R, magnitude of P, times this angle between them, right? But remember, I don't want the angle in my equation. I mean, this is true, but I don't want it. I want to get rid of that theta. Well, we can do all sorts of fun things with math, right? Let me just write that differently. Let me just write it like R sine theta times P. Okay. Well, what is R sine theta? Look at the picture. What's R sine theta? It's just this guy, right? Opposite. So it's R perp. So it's just R perp times P, which is the same thing as R perp times mv. So that's another equation, right? That's the magnitude, right? The magnitude. So we can, there it is, right? So the magnitude is R perp times mv. And again, it's nice, because this is regular momentum, translation or linear momentum. You just get that R perp in there. Okay, that's cool. Now, there's another equation, which is what we're going to use a lot. But you can only use it in certain special situations. So this is a symmetrical rigid body, right? It's a disk. It's a uniform disk. So if you have a symmetrical rigid body, and it's rotating about its center of mass, so here's the axis through the center of mass. So if you have all that stuff going on, right? Symmetrical rigid body rotating about the center of mass, here's the equation. L equals I omega. Now, I hope you understand. That's totally awesome. I've been doing this little trick, right? Like what's the angular version of P, L? What's the rotational version of M, I? What's the rotational version of V, omega? It doesn't work all the time, but it works here, right? You have a symmetrical rigid body rotating about the center mass. L equals I omega, just like P equals mv. So that's wonderful. So yeah, so we use this one a lot. But, you got to know how to do this one too, right? Okay. Now, what was so great about linear momentum? It was conserved, remember? If you had an isolated system, linear momentum was conserved. Well, Doesn't that, so if that's true, perhaps angular momentum is conserved if it's an isolated system. Doesn't that kind of make sense? So let's talk about that. Let's talk about conservation of angular momentum. Okay, we'll start off with this. Remember that? Newton's version of F equals ma? Right? This is F equals ma. So the sum of the forces equals ma, which is dp dt. Okay? And again, if you're in deep outer space and you throw something, after you let go, there's no forces on it, so the momentum is constant. So so the velocity never changes. Or you can say that the change in momentum is zero, however you want to look at it. All right? So here, isolated system, deep outer space, sum of the forces is zero. So this derivative is zero. If the derivative is zero, the p is constant. Good old calculus, right? Okay, well, so but we want to do we want to get a rotational version, right? We want to get a rotational version. So what do you say? Let's just guess, all right? So here we have sum of the forces equals dp dt. So just guess. What do you think the rotational version of that equation is? Just guess. Well, what's the rotational version of force? Torque. What's the rotational version of P? L. Right? So that's just a guess. Turns out it's true, but all right. But let's just check it out. I mean, you know, you can't guess all the time, right? Let's actually see if this is correct. All right. So we want to see if that's correct. And it's kind of fun to do the math. All right. So we want to see if dl dt is torque. Okay. So here we go. So dl dt. All right. Well, what's L? You know. So this is d dt. What's L? What did I just tell you? L is that horrible thing. R cross P. Okay? So L is R cross P. Well, how do you take the derivative of a vector cross product? Well, it's just like the product rule. You know, first times, second, all that bit. So it's the same. You know, it's not a big deal. All right. So it's a product rule, only with a cross product. So it's dr dt cross P plus R cross dp dt. Ah, doesn't that remind you of the product rule in calculus? Hope so. Okay, now let's work with this. What's dr dt? Velocity. All right. What's momentum? mv is a plus. Okay. So this I could write this as m v cross v, right? Well, v cross v, what's that? Well, what's the cross product? It has a sign in it. What's the angle between a v and a v? 0. What's the sign of 0? 0. So what is this term? 0. All right, that's 0. Okay? And what's dp dt? Force, right? Force. dp dt is force. So what's r cross f? Torque. So what do you know? We just proved it, right? So dl dt equals torque. All right? So we proved it. I didn't have to write the sum, but anyway. All right, well, I will, whatever. So the sum of torque equals dl dt. Okay? So if we have an isolated system, which means that the sum of the torques equals 0, that means that dl dt equals 0. If the L dt is 0, that means that L is constant, right? So there you go. All right, so it's similar to this, you know. If here's the equation. Torque equals dl dt. If you have an isolated system, the sum of the torques are 0. So that means that the derivative is 0. That means L is constant. So angular momentum conservation. Incredible, right? Incredible. Okay, oh boy, let's see if this will work. So here's a really cool demonstration, but I didn't want to do it. I always have a student do it, but because I don't want to do it. I don't have good balance. Come on. Ah, crumb. Come on, what's your problem? Come on. Hold on. Yes. Okay, now let's see. If you can't hear it, it's not a big deal. Just watch.
Demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin.
Okay, wait.
I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length.
Is that too loud or is that okay? All right, let me just start over. All right, so he's going to demonstrate conservation of angular momentum.
We can demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin. I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
All right. So like I say, I usually do that in class. I don't have one of those chairs that the guy sits on. I have a turntable. And so I have a student stand on the turn. Well, I'll show you in a minute as soon as I get this slide. Good golly, you're slow. Okay, so what we do in class is kind of like this. So I have a turntable, and I have a student, and the student has dumbbells. And so we get the student rotating. And then I tell the student, go like this. And as soon as the student does that, starts going really, really fast. Right? And then I tell the student, go like this. And then he slows down. Or he or she, whatever. Just like the guy, basically, you know? Okay, so what's going on? How do you explain that? Right? First the guy is kind of going slowly, then super fast, and then back to slowly again. And if you have no friction, it would just keep going, right? It kind of looks like something's conserved, So think about it. If this thing is frictionless, are there any external torques? If it's frictionless? No. All right. Well, look at that. If there are no external torques, L is constant, right? So here we have a situation where L is conserved. Now, we had all those different equations for L. Which one are we going to use? Well, this is a nice situation. This is a symmetrical, rigid body, and we're rotating it through the center of mass. We're going to assume that the person is symmetrical, rigid body, and we're going to rotate through the center of mass, right? So guess what equation we can use? We can use a nice one. We can use L equals I omega. Okay, so we can use L equals I omega. So I omega is constant. Right? Awesome. I omega is constant. Okay, so look. So that means I omega here has to be I omega here. But which one has the larger I? Remember, I is the sum of mr squared. So here, you know, we have the dumbbells really far away from the rotation axis. So it's large I. Here, we have the dumbbells really close to the rotation axis, so it's small I. So here, large I, small I. So look, we have large I, small omega, but now if I shrinks, what has to happen to omega? It has to increase. There you go. So that's why it works. If you've watched the Winter Olympic Games, you know, you've watched the figure skating, and you know the figure skaters at the end, you know, they do this. Then all of a sudden they do this. What happens? They start going really, really, really fast. That's why. Angular momentum conservation. So that's pretty cool, don't you think? Okay, now notice though, there's more to it, right? This is really a vector equation, right? That's a vector equation, you know? And so if you want to change the magnitude or the direction of L, you have to apply a torque, right? Magnitude or direction. Let's quit. Let's quit for the